In a 220/110-volt 3-phase 4-wire system which is Y-connected with a neutral, the neutral conductor is also referred to as the grounding conductor or earth. The neutral conductor must be bonded to the ground electrode of the premises, such as a building or house. This bonding creates a low resistance path for fault currents to flow, which is a crucial aspect of electrical safety. Moving on to a 220/110-volt 3-wire system, this is typically a single-phase transformer connected in a way that it can be viewed as an open delta configuration because of its derived neutral. In this configuration, there isn't a true neutral point in the traditional sense. Instead, the transformer creates what's known as a floating neutral or a derived neutral. The derived neutral should not be connected to the grounding electrode of the premises. This arrangement is known as a floating neutral system. Considering some additional points for the 3-phase 4-wire system, the voltage between each phase in neutral is 110 volts, while the voltage between any two phases is 220 volts. In the 3-wire system, the voltage between the two hot wires is 220 volts, and the voltage between the hot wire and the derived neutral is approximately 110 volts. It's important to recognize that the neutral conductor in the 3-phase system carries the return current from all three phases. In contrast, in a 3-wire system, it carries the current from any unbalanced loads. Proper grounding is absolutely essential for electrical safety. It provides a safe path for fault currents, which prevents electrical shocks and ensures the reliable operation of electrical equipment. Grounding is a critical safety measure in electrical systems for several important reasons. Firstly, it provides a low impedance path for fault currents to return to the source. This low impedance allows for a large fault current to flow quickly, which in turn causes the overcurrent protection devices, such as circuit breakers or fuses, to trip and disconnect the faulty circuit. This rapid disconnection minimizes the risk of electrical shock, fire, and equipment damage. Secondly, grounding helps to maintain a stable voltage level within the electrical system. By connecting the neutral point of a system to ground, the voltage between any phase conductor and ground is limited to a safe level. This prevents voltage fluctuations and reduces the risk of insulation breakdown, which can lead to faults and equipment failure. Thirdly, grounding provides a reference point for voltage measurements. By establishing a common ground potential, technicians and electricians can accurately measure voltages within the system. This is essential for troubleshooting and maintenance purposes. Now let's delve into the specific grounding requirements for different types of systems. In a 3-phase 4-wire Y-connected system, the neutral point of the Y connection is intentionally grounded. This provides a direct path for fault currents to return to the source, ensuring that overcurrent protection devices operate quickly and effectively. The grounding electrode, which is typically a ground rod or a metallic water pipe, is connected to the neutral point of the system. The size of the grounding conductor and the grounding electrode must comply with the National Electrical Code, or NEC, requirements. The NEC provides specific tables and guidelines for determining the appropriate size of grounding conductors based on the size of the service entrance conductors. The NEC also specifies the minimum size and depth of ground rods, as well as the requirements for bonding different metallic components within the electrical system. Bonding ensures that all metallic parts are at the same potential, which further reduces the risk of electrical shock. In a 3-wire single-phase system derived from an open delta transformer, the grounding requirements are different. As mentioned earlier, this type of system has a derived neutral, which is not a true neutral point. Instead, it's created by tapping the midpoint of one of the transformer windings. The derived neutral is typically not grounded directly. Instead, it's allowed to float. This means that there's no intentional connection between the derived neutral and ground. The reason for this is that grounding the derived neutral can create a circulating current path, which can lead to overheating and equipment damage. However, it's important to note that even though the derived neutral is not directly grounded, the equipment grounding conductors still need to be properly installed. The equipment grounding conductors are connected to the metal enclosures of electrical equipment and provide a path for fault currents to return to the source in the event of a ground fault. The equipment grounding conductors must be sized and installed in accordance with the NEC requirements. They must also be bonded to the grounding electrode system, which ensures that all metallic parts are at the same potential. In addition to the grounding requirements for the neutral and equipment grounding conductors, there are also specific requirements for bonding different metallic components within the electrical system. Bonding is the process of connecting all metallic parts together to create a continuous electrical path. This includes metal conduits, metal enclosures, metal water pipes, and other metallic components. The purpose of bonding is to ensure that all metallic parts are at the same potential, which minimizes the risk of electrical shock. The NEC provides detailed guidelines for bonding different types of metallic components. These guidelines specify the size of the bonding conductors, the methods of making connections, and the requirements for bonding different types of equipment. It's important to follow these guidelines carefully to ensure that the bonding system is effective. Now let's talk about the importance of using the correct wiring methods and materials. The NEC specifies the types of wiring methods that are permitted for different applications. These wiring methods include rigid metal conduit, electrical metallic tubing, flexible metal conduit, and non-metallic conduit. The choice of wiring method depends on several factors, including the environment, the type of occupancy, and the electrical load. It's important to select the appropriate wiring method for the application to ensure that the electrical system is safe and reliable. The NEC also specifies the types of conductors that are permitted for different applications. Conductors are typically made of copper or aluminum and are insulated with various types of materials, such as polyvinyl chloride, or PVC cross-linked polyethylene, or XLPE, and rubber. The choice of conductor depends on several factors, including the voltage, the current, and the temperature. It's important to select the appropriate conductor for the application to ensure that the electrical system is safe and reliable. In addition to the wiring methods and conductors, there are also specific requirements for overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. They work by interrupting the flow of current when it exceeds a predetermined level. The NEC specifies the types of overcurrent protection devices that are permitted for different applications. It also specifies the size of the overcurrent protection devices based on the size of the conductors and the electrical load. It's important to select the appropriate overcurrent protection devices for the application to ensure that the electrical system is safe and reliable. Now let's discuss some common mistakes that people make when working with 220/110 volt electrical systems. One common mistake is to misidentify the neutral conductor. The neutral conductor is typically identified by its white or gray color. It's important to always verify the identity of the neutral conductor before making any connections. Another common mistake is to improperly ground the electrical system. Grounding is essential for electrical safety, and it's important to follow the NEC requirements carefully. A third common mistake is to use the wrong size conductors or overcurrent protection devices. The NEC provides specific tables and guidelines for determining the appropriate size of conductors and overcurrent protection devices. A fourth common mistake is to fail to properly bond metallic components within the electrical system. Bonding is essential for preventing electrical shock, and it's important to follow the NEC guidelines carefully. Finally, a fifth common mistake is to work on electrical systems without proper training and qualifications. Electrical work can be dangerous, and it's important to have the necessary knowledge and skills to do the job safely. Let's explore the practical implications of these systems in residential and commercial settings. In a typical home, a 220/110 volt single-phase system is used to power appliances and lighting. The 220 volt circuits are typically used for large appliances, such as electric stoves, clothes dryers, and air conditioners. The 110 volt circuits are used for smaller appliances, lighting, and other general-purpose outlets. In a commercial building, both 220/110 volt single-phase and 208/120 volt or 480/277 volt three-phase systems may be used. The three-phase systems are typically used to power larger equipment such as HVAC systems, motors, and industrial machinery. The single-phase systems are used for lighting, general-purpose outlets, and smaller appliances. When designing or installing a 220/110 volt electrical system, it's important to consider the load calculations. Load calculations are used to determine the amount of power that will be required by the electrical system. This information is used to select the appropriate size conductors, overcurrent protection devices, and transformers. The NEC provides detailed guidelines for performing load calculations. These guidelines take into account the type of occupancy, the size of the building, and the types of electrical equipment that will be used. It's important to perform load calculations accurately to ensure that the electrical system is able to handle the expected load. Another important consideration is voltage drop. Voltage drop is the decrease in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The NEC provides guidelines for limiting voltage drop. These guidelines specify the maximum allowable voltage drop for different types of circuits. It's important to select conductors that are large enough to minimize voltage drop. In addition to these considerations, there are also specific requirements for wiring different types of equipment. For example, there are specific requirements for wiring electric motors, HVAC systems, and lighting fixtures. The NEC provides detailed guidelines for wiring different types of equipment. It's important to follow these guidelines carefully to ensure that the equipment is wired safely and correctly. Now let's discuss the importance of regular maintenance and inspection of 220/110 volt electrical systems. Regular maintenance and inspection can help to identify potential problems before they become serious. This can prevent electrical shocks, fires, and equipment damage. Some common maintenance tasks include checking for loose connections, inspecting for damaged wiring, and testing overcurrent protection devices. It's also important to keep the electrical system clean and free of dust and debris. Regular inspection of the electrical system should be performed by a qualified electrician. The electrician will inspect the wiring, grounding system, overcurrent protection devices, and other components of the electrical system. They will also perform tests to ensure that the electrical system is operating safely and correctly. If any problems are found, the electrician will recommend repairs or replacements. Let's consider some specific examples of how grounding works in different scenarios. Firstly, imagine a metal enclosure that houses electrical equipment. If a live wire comes into contact with the metal enclosure, it can create a dangerous shock hazard. However, if the metal enclosure is properly grounded, the fault current will flow through the grounding conductor back to the source. This will cause the overcurrent protection device to trip, disconnecting the circuit and preventing an electrical shock. Secondly, consider a lightning strike. Lightning is a powerful surge of electricity that can damage electrical equipment and cause fires. However, if the electrical system is properly grounded, the lightning current will be safely diverted to ground, minimizing the damage. The grounding electrode system provides a lower impedance path for the lightning current to flow to ground. This helps to protect the electrical system and the building from damage. Thirdly, imagine a situation where there is a buildup of static electricity. Static electricity can build up on objects and surfaces, especially in dry environments. If a person touches an object with a buildup of static electricity, they can experience an unpleasant shock. However, if the object is properly grounded, the static electricity will be safely discharged to ground, preventing the shock. The grounding system provides a path for the static electricity to dissipate, preventing it from building up to a dangerous level. Let's also consider some common misconceptions about grounding. One common misconception is that grounding is only necessary for safety. While safety is the primary reason for grounding, it also provides other benefits such as improving the performance of electrical equipment and reducing electrical noise. Another common misconception is that any ground is a good ground. A proper grounding system must be designed and installed in accordance with the NEC requirements. A poorly designed or installed grounding system can be ineffective or even dangerous. A third common misconception is that grounding is only necessary for new construction. Grounding is important for both new and existing electrical systems. Existing electrical systems should be inspected to ensure that they are properly grounded. If the grounding system is inadequate, it should be upgraded to meet the current NEC requirements. Now let's discuss some of the advanced grounding techniques that are used in specialized applications. One advanced grounding technique is the use of isolated ground receptacles. Isolated ground receptacles are used in sensitive electronic equipment, such as computers and medical devices. These receptacles have a separate grounding conductor that is isolated from the building's grounding system. This helps to reduce electrical noise and improve the performance of the equipment. Another advanced grounding technique is the use of surge suppressors. Surge suppressors are used to protect electrical equipment from voltage surges. These devices work by diverting the surge current to ground, preventing it from damaging the equipment. Surge suppressors are commonly used to protect computers, televisions, and other electronic devices. A third advanced grounding technique is the use of equipotential bonding. Equipotential bonding is the process of connecting all metallic parts in an area together to create a common electrical potential. This helps to prevent electrical shock hazards in areas where there is a risk of contact with water, such as swimming pools and spas. Equipotential bonding is also used in hospitals and other healthcare facilities to reduce the risk of electrical shock to patients. In addition to these advanced grounding techniques, there are also specific grounding requirements for different types of equipment. For example, there are specific grounding requirements for generators, transformers, and electric motors. The NEC provides detailed guidelines for grounding different types of equipment. It's important to follow these guidelines carefully to ensure that the equipment is grounded safely and correctly. Let's delve a bit deeper into understanding grounding electrode systems. The grounding electrode system is the foundation of the entire grounding system. It provides the connection to the earth, which is used to dissipate fault currents and maintain a stable voltage potential. The most common types of grounding electrodes are ground rods, metal water pipes, and concrete encased electrodes, also known as UFA grounds. Ground rods are typically made of copper or copper-clad steel and are driven into the ground to a depth of at least 8 feet. The number and spacing of ground rods are determined by the NEC requirements. Metal water pipes can also be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet. However, plastic water pipes cannot be used as grounding electrodes. Concrete encased electrodes are typically used in new construction. They consist of a length of bare copper conductor that is encased in concrete. The concrete must be in direct contact with the earth. The size and length of a concrete encased electrode are determined by the NEC requirements. The grounding electrode system must be properly connected to the building's electrical system. This is typically done by connecting the grounding electrode conductor to the main grounding busbar in the electrical panel. The grounding electrode conductor must be sized in accordance with the NEC requirements. It's important to protect the grounding electrode system from damage. Ground rods should be protected from physical damage, such as being struck by vehicles or equipment. Metal water pipes should be protected from corrosion. Concrete encased electrodes should be protected from damage during construction. Regular inspection of the grounding electrode system is essential to ensure that it is in good condition. The grounding electrode system should be inspected for corrosion, damage, and loose connections. If any problems are found, they should be repaired immediately. Let's also touch upon the importance of proper labeling and documentation of the grounding system. Proper labeling and documentation can help to ensure that the grounding system is properly maintained and that it is easy to troubleshoot any problems. The electrical panel should be clearly labeled to indicate the location of the grounding electrode conductor and the grounding busbar. The grounding electrode system should also be documented in the building's electrical drawings. The documentation should include the type of grounding electrodes that are used, the location of the grounding electrodes, and the size of the grounding electrode conductor. It's also a good idea to keep a record of any maintenance or repairs that are performed on the grounding system. This information can be helpful for troubleshooting problems in the future. Finally, let's reiterate the importance of consulting with a qualified electrician when working with 220/110 volt electrical systems. Electrical work can be dangerous, and it's important to have the necessary knowledge and skills to do the job safely. A qualified electrician can help to ensure that the electrical system is installed and maintained in accordance with the NEC requirements. They can also help to troubleshoot any problems that may arise. Consulting with a qualified electrician is especially important when working with complex electrical systems such as three-phase systems and systems with specialized grounding requirements. A qualified electrician can provide valuable guidance and expertise to ensure that the electrical system is safe and reliable. By following these guidelines and consulting with a qualified electrician, you can help to ensure that your 220/110 volt electrical system is safe, reliable, and efficient.